This is a brief demonstration of the propane dehydrogenation with integrated CO2 capture process to produce propylene given by Khalid.j. Propylene is used in the production of a wide variety of applications that directly influence our daily lives. Those applications include the making of fibers, textiles, vehicle parts, packaging materials, and producing electrical devices. These overarching utilities made it the second most important petrochemical feedstock.
In the chemical industry, 80% of the energy consumed and 75% of the greenhouse gases emitted are accounted for by merely 18 products. In the graph presented, the size of the bubbles corresponds to the relative emissions of CO2. Here, ammonia production is the most polluting chemical process, followed by ethylene production, then methanols, and after them comes propylene, thereby illustrating that propylene production is prime among the polluting processes.
Currently, propylene is mostly produced as a byproduct in the production of ethylene through steam cracking or as a byproduct of gasoline production processes. These processes are energy intensive and highly emissive, making them unsustainable. Moreover, the current approach of producing propylene will no longer be sufficient to meet the ever-growing demand. By the year 2030, for example, it is projected that the demand for propylene will exceed what conventional methods can supply by 12 to 14%. To fill the gap between the supply and demand, it is necessary to construct on-purpose propylene production plants as opposed to by-production plants. This provides an opportunity for the adaptation of new and greener propylene production technologies. In this video, we will compare different propylene production routes for a new plant which will then be enhanced with CO2 capture technology to minimize any adverse environmental effects.
There are three different routes for the direct production of propylene that have achieved technological maturity, so we will limit our discussion to them. First, we have propane dehydrogenation process, or PDH for short, which requires propane as the input. This process relies on direct reduction of propane, so it does not produce larger hydrocarbons, unlike the other processes presented. The second two processes are methanol to olefins, or MTO, and methanol to propylene, or MTP. Both processes have methanol as the input and produce the same major products, and both have cracking steps within them. Still, the technologies used in each are distinct enough that they are distinguished in the literature. Based on the output alone, propane dehydrogenation is favored. This is because it requires less separation steps due to the smaller number of products, thereby saving costs needed for separation. Indeed, propane dehydrogenation is known to have comparatively low operating costs. Another point of comparison is percentage of propylene selectivity, which represents the molar percentage of propylene in the output. Representative values from the literature were obtained for each process to conduct this comparison. The values in the table here show that propane dehydrogenation process is by far superior in terms of selectivity. This is expected since it produces fewer types of products, as we have indicated. Therefore, the discrimination to favor the production of propylene is easier, since the reaction network is less complex. It is worth noting that the values of selectivity alone do not discount the appeal of the methanol to olefins and methanol to propylene processes economically. This is because most of the byproducts are valuable in the market. However, since our goal is primarily to produce propylene, the propylene dehydrogenation process is also favored in this front. Therefore, PDH will be our chosen process. With propane dehydrogenation chosen, the next step is to augment it with a suitable CO2 capturing technology. There are two main paths that can be taken, capturing by adsorption or absorption. We opted for adsorption because absorption have limited capacity for CO2, and it incurs extra expenses by consuming a large amount of energy and by corroding the equipment. Within adsorption technologies, there are two main routes, which are based on amine grafting or amine impregnation. Both methods are comparable and are viable for our process. However, propane dehydrogenation lends itself to an easier implementation of an amine impregnation method. Specifically, there is an emerging novel technology that utilizes supercritical propane to capture CO2 without consuming propane. Therefore, some propane can be directed from the feed to be utilized in CO2 capture, and after its use, it can be recycled back to the feed, thereby eliminating the need for additional material costs for the process.
The operation of a plant of this type results in the emissions of several greenhouse gases. Our primary concern is sulfur dioxide, which hinders plant growth at high concentrations. Sulfur dioxide can also react in the atmosphere, forming compounds that reduce visibility. The haze this creates has been a problem affecting many national parks and wilderness areas in the United States. Furthermore, short-term exposure to sulfur dioxide can harm the respiratory system and make it difficult to breathe. People with asthma, in particular children, are sensitive to these effects of sulfur dioxide. Nitrous oxide is another harmful compound that this process generates. It, alongside sulfur dioxide, contributes in the formation of acid rain. When acid rain falls, it completely destroys sensitive ecosystems. All of this shows that the process will have an adverse effect on the surrounding communities and environment. Therefore, utmost care must be taken to minimize these effects. The propane dehydrogenation plant requires high operating temperatures of around 600 Celsius in the reactors. These high temperatures require proper insulation to protect the equipment surrounding the reactor. Operating pressure, however, is relatively low, and it will not introduce any additional hazards. Another safety concern is the high flammability of supercritical propane, as its presence increases the danger of any potential leak that might introduce oxygen to the streams where supercritical propane is passing. Therefore, utmost care must be taken to prevent such occurrence.
As an initial evaluation of the profitability of the process, we conducted an input and output analysis. We assumed a conversion factor of 0.92 and propylene selectivity percentage of 0.93. Both values were obtained from the literature for similar propane dehydrogenation processes. For the prices used in the calculations, we assumed that the plant is based on the United States Gulf Coast due to the availability of cheap feedstock in that area. We then used the shown prices to calculate the profit based on the input and output values, which is calculated to be $258 million. If we impose a requirement of a minimum rate of return on investment of 10%, the maximum allowable capital investment would be $2.58 billion. Williams, a US company whose core business deals with processing natural gas, have started a project for making a similar PDH plant. Their estimated investment is $638 million, which is well below the capital investment we calculated. Using their estimation as our capital cost, we have calculated our actual rate of return to be 40%, making the endeavor economically very appealing. To account for errors in the capital investment estimation, we conducted a sensitivity analysis for the rate of return on investment, where the capital investment was varied within 25% of its value. With this variation, the rate of return moved from 54% to 32%, which is still financially viable. Additionally, a sensitivity analysis for the prices was made, with the variation being within 25% of the price. Since ethylene is a minor product, the rate of return is almost insensitive to its price changes, as the plot here shows. On the other hand, changes in propane and propylene prices can be significant. For 25% decrease in the price of the products, coupled with 25% increase in the price of the reactants, the rate of return is slightly above 10%, showing that the process remains profitable even under the most unfavorable prices.
The main revenue stream for our process is propylene. However, since propylene has a multitude of uses in different industries such as the automobile, clothing, and tech industry, it will not react heavily to a shift in a single market, making its selling price more stable. Still, in the unlikely case where the price of propylene drops below that ethylene, the process has the capacity to shift production towards making more ethylene instead.
Of the three processes presented, propane dehydrogenation is chosen due to its superiority in terms of propylene selectivity and lower operating costs. The process is financially appealing with an estimated rate of return of 40% based on an input-output analysis. For this reason, Bayer Chemical Corporation can likely profitably acquire a market share of this section of the industry, taking advantage of the aforementioned supply and demand gap. It is important to note that although a PDH plant produces several compounds that have an adverse effect on the environment, their amount can become insignificant if the plant was constructed with a sustainable design that employs emission reduction and capturing technologies. We thus recommend the commission of the next phase of the project by pursuing a detailed process design and economical analysis. This concludes the film. Thank you for watching.